Yeah. All right. So I think today's our fourth lecture, which sort of blows my mind. We're going to start going over chapter 2, and hopefully we'll see how far we can knock that out. So what we're going to start with is sort of an extension of what we already learned about variables and stuff like that. And the big question is, where do these variables come from? So we'll talk about variables, or these measurements coming from some sort of experiment. And in this case, the experiment doesn't have to be like a traditional trial or like scientific experiment that we think of. It can be something much broader as long as there's some sort of uncertainty around it. Now, there's certainly different ways of setting up an experiment. We can talk about flipping a coin, right, each time. That could certainly be an experiment. The experiments could be complex in nature. So not just flipping one coin and seeing what you get. It could be like, let's flip a coin until we get heads, right? Similarly, we can talk about pulling cards for a deck. Another interesting one is like weighing a loaf of bread, right? You might weigh that loaf of bread multiple times, and each time you do it, get a different answer, okay? So we see these experiments generating randomness in different ways, right? So for the loaf of bread example, we get randomness by the process of weighing the bread, right? While later on, let's say we're measuring the strength of different steel beams, we get randomness by the fact that we're measuring actually different steel beams, right? So each time we run an experiment, what we end up with is a sample space, right? This sample space sort of dictates what are the available options that we could generate in the experiment. So flipping a coin, it's pretty straightforward. Our sample space is just heads or tails. Flipping a coin 3 times, right? You're going to create these tuples, right, of all the different ways you could flip a coin 3 times, right? Heads, 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 tails, heads, tail, heads, all the way through. So you should have about 8 options here, right? Oops, that's a caterpillar. We can talk about rolling 2 dice and adding them up, right? We can talk about rolling 2 dice and keeping these values separate. The other interesting one that I always like is flipping a coin until we get heads. Because this, if you look at these sample spaces, they have one unique trait. Actually, well, there's actually 3 unique traits here. One is that all these sample spaces are finite sized, right? So this one has 36 elements in it. This rolling 2 dice has 12 elements. Flipping 3 coins has 8. Flipping 1 coin has 2. Okay. But if we look at this experiment right here, where we ask, how many times can I flip a coin until I get heads? This sample space is actually infinitely large. Okay. So you could think about it as the first way that you could get heads, right, is you just get it right off the bat. Right? The other way that you could flip a coin until you get heads is tail heads, right? So you flip a tail once, and then you follow up with the heads. Or you could flip tail, tail, heads, or tail, 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 heads, tail, 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 heads, ... right? You could throw 1 million tails and then get a heads. Granted, that event of flipping 1 million heads and then getting, or 1 million tails and then getting a head is extremely rare. It's still part of the sample space. Okay? So there's nothing that says our sample space can't be infinitely large. Now, the interesting thing about these types of sets, so there's a good example of one, and it'll come up over and over again. These are what we call countable sets. So even though they might be infinitely large, we can actually count them off or list them off. An uncountable set would be all the numbers between 0 and 1, right? All the real numbers. Because you can't list every single one. But if you can list every single element in the set, then it's considered a countable set. Right? So these sample spaces, example sample spaces for different experiments, they have two things in common. One, they're all countable, right? Two, they're finite sized. But remember, that doesn't need to be the case. These were just sort of toy examples I gave. We just gave one case where we had a countable yet infinitely large set. And certainly you could imagine weighing a loaf of bread. Maybe I can generate, or not generate, every time I weigh a loaf of bread, it will come back between, let's say, I don't know, 200 grams and 300 grams. Okay, based on the accuracy of my scale and who's reading it. And so in that case, I have a continuous set, right? My sample space is continuous. And so the important part here is that our sample space contains in it all possible outcomes. Now, later on we'll leave it like that. Okay. For now, I think we're going to mostly focus on events that are sample spaces that are countable. And they sort of make the math a little bit nicer as we sort of proceed with our discussion. Okay? Any single subset of that sample space is called an event. Okay? So a simple event is one that only contains one outcome. Right? So a simple example for the rolling 2 dice experiment would be rolling a 10 or rolling a 6. Okay? Those are simple events. A compound event contains multiple outcomes. All right? So this event, a compound one might be rolling a 6 or lower. Okay? And so the reason it's compound is because it's actually generated by a bunch of different events. One is rolling a 1, 2, 3, 4, 5, and 6. Okay, so that's kind of what makes it a compound event. Certainly we can look at this case for the flipping of 2 coins. Right? So a simple event would just be the event of flipping heads. Okay. Here what I've done is I've defined examples of 3 different compound events. One of them is flipping at least one head. And what we see is that event space has 3 different simple events contained in it. Now, we could just change the wording of our event. So not flipping 2 tails, right? And we still have the same event set, right? So even though the event sets might be defined differently, they can still be equal to each other. And so there's other sorts of logic that we can run. So like flipping at most 1 head. All right. So the way we go about creating these more complex events or these compound events is usually through the use of set theory, I guess. So probability and set theory go sort of hand in hand. Because really that's all that these events are, right? So we're starting off with some sample space, which is a set, right? So if you don't know what a set is, it's basically just a list of objects, right? And usually we denote it with curly braces on both sides. And the subset is just taking some of those elements out and defining its own set. Okay. So Usually we have three basic operations when we're talking about sets. Okay. So the first one is the complement. So when we're talking about events, so let's say set A contains a bunch of events. The complement of A is all events that are not in that set. Right, so for this example, the one we had around here, so if our set A was defined as flipping two heads, all right, which is in fact given by head, head, then A complement would be everything else that could possibly happen except flipping two heads, which is in fact the case that we have here. Oh, sorry, two tails. My bad. Two tails. So we'd have head, 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 tails, and tail heads. Okay. That should say intersection. The other two operations that we usually use are union and intersection. Okay. And so what we're saying is we're trying to combine events by saying either event A happens or event B happens, right, which is the union. Or we could say something like event A happens and event B happens, so everything within it. Okay, so let's go through a couple examples. So let's say we have an experiment, and I don't know, we have the sample space S where our options are 1, 2, 3, 4, 5, 6, right? We can define event sets A, B, and C. So maybe I have a 7-sided dice or a random number generator that produces a number between 0 and 6 integers, right? And I say event A is getting 0, 1, 2, 3, or 4. Event B is getting 3, 4, 5, or 6. And event C is 1, 3, or 5. All right, so, you know, maybe C is like, let's say that, again, 7-sided die, which doesn't exist, I don't think. But event C is like rolling an odd number, right? While event A is just rolling a number less than or equal to 4. And then B is rolling a number between 3 and 6. Right? Okay, so we can apply a bunch of these operations. So if I wanted to know what the complement of A is, it's just everything that's not in the set, but is in our sample space. So the only thing that's not in A is 5 and 6. Okay, so that's pretty easy. When we talk about union, what we're doing is we're joining two sets. So I could say something like A union B, and I want to find all the elements that are in A or B. Right? So that's going to be 1, 2, 3, 0, 1, 2, 3, 4. We have 3 repeated, 4 repeated, 5 and 6. And so we just stick everything in, and we don't have to worry about the repetitions. Right? So in sets, we don't actually keep track of the counts. So A union B is in fact covers our whole sample space, right? Yeah. We could also do A and B. And in this case, we're just trying to find the common elements that are both in A and in B. All right, so that would involve rolling let's say a 3 and 4, because we see them both in A and B. Okay. So in this way, we can start generating compound or more complex events to test for when we're calculating our probabilities down the road. Oh yeah, this is a fun one, right? A intersection C complement. Of course, we can apply these in sort of a combination, right? So if we wanted to, we could do A intersection B union C, all complemented, right? And we would just apply an order of operations and just try to be careful about it. So I think actually order of operations is sort of the same as with math, with basic arithmetic. So I think this guy goes first. So first you go prime, then intersection, then union, unless it's noted. But really you should be clarifying what the order of operations here is. So here we'll calculate this guy first, and then we'll union it with C, and then we'll take the complement of it. So, so this is basic process. All right. Now, we do have a special set, which is the null set. And so the null set is basically the empty set, right, where there's nothing inside of it. All right. And this actually happens quite frequently, right? So this equivalent would be, let's say, I don't know, D is equal to 5, the set 5, and actually no, let's make it 4. 4. And then I asked, what is C intersection with D? In this case, C has the values 1, 3, 5, which are odd numbers. And if I try to intersect it with 4, they have nothing in common. So the return is just the null set or the empty set. Okay, so where does this happen? What's the probability you get an A and a D in this class? 0, right? You can't get both grades at the same time. You can only get one, right? And so a lot of times you'll see the null set occur two ways. One is you have an ill-formed logical definition for some sort of event, or there's maybe just a sequence of events that are impossible, right? So what's the probability of playing 5 games in the World Series if you win the first 4 games? Okay, so for those of you who don't know, World Series is a best of 7 series. So if you win 4 games, you're not going to play the 5th game. And so it sort of works out like that. Now, when we have this relationship where A and B, any two sets where we find the intersection between them, all right, if it's equal to the null set, we say A and B are mutually exclusive or disjoint. All right? And this ends up being a really nice property that will make our mathematics quite easier down the road. So one way we can do this is if we go back to our World Series example, and we talk about, what is the probability you win the World Series in 4 games, or 5 games, or 6 games, or 7 games? And each one of those events, winning in 4 games, winning in 5, winning in 6, winning in 7, are disjoint events, right? They don't overlap with each other. You either win in 4, or you win in 5, or you win in 6, or you win in 7. Okay. If I can calculate the probability of winning in any number of games, then I can actually say something like, what's the probability of winning the World Series, right? Well, yeah, kind of, sort of. Yeah, I'm going to skip that. And so one way that we can sort of visualize these ideas are using Venn diagrams. Have most of y'all worked with Venn diagrams? Yeah, okay. I think it's pretty good. It works out pretty well. Just be careful on when you apply them. Yeah, be careful. Sometimes they get applied inappropriately. Okay, so usually these Venn diagrams are a good way to start thinking about event sets and logic. So typically we'll think of our two sets, A and B. right? And so we draw our little circles. And if we're talking about things they have in common, what we're referring to is the area sort of between them and any event that lies in that common area, right? So before, let's see if I can remember this, 3, 4, 5, 6. So in this problem, we had 0, 1, 2, 3, I think in A exclusively. Oh, no, 0, 1, 2. Okay. Inside this area between them, we had 3 and 4. And then inside B, we had 5 and 6. Okay. And so when we said A intersection B, what we are doing is we are interested in the values 3 and 4. Okay. A union B is everything that's contained in both. Right? A complement is everything outside of A. Right. Again, mutually exclusive, the idea is they share nothing in common. Right? It's really nice when you have your set S, so this is your sample space, and A takes up 1/2, not necessarily proportionally 1/2, but let's just say one part of S, and then B takes over everything else, right? That's really, really nice, which is effectively A and A complement, right? So in this case, B is equal to A complement. This is a really nice way. It makes our math a lot easier. Of course, we can start talking about 3 sets, right? 4 sets, 5 sets, whatever you want. Okay, so this is a good way of visualizing what we're doing in terms of sets. All right. So this is actually my favorite part. Okay, so I'm going to talk about axioms and properties of probability. For those of you who don't know, axioms are sort of like the minimum set of rules that you need to define a branch of mathematics. Okay? And the idea is that basically anything you'll learn in probability from this point forward actually derives from just 3 axioms, which is really, really neat. And so for us, when we talk about experiments and sample spaces and events, our goal is going to be, so for some event A, we want to calculate the probability of that event occurring. We want to give it some sort of measure of likelihood. Now, in defining this concept of the probability of an event, all we need are 3 basic rules. Again, this blows my mind. I think it's so cool. So first is that the probability of any event is greater than or equal to 0. Okay, so we can't have negative probabilities. The next one is that the probability of our sample space, so the probability of all events that could ever happen is 1. Okay, these two actually don't seem so crazy because they're essentially bounding our probability between 0 and 1. Like, the fact that these 2 rules account for 2/3 of the axioms, I find astonishing. Okay, because they really, they say a lot, but they don't say much at all. I think it's pretty easy to understand. Okay. The last rule is kind of neat. Okay. So the last rule basically says if you have a bunch of disjoint events, so an infinite collection of them, in fact, if I try to find the union of all these disjoint events, it's just equal to the sum of the probability of each event. Okay. That? Excuse me? No, I think you're going to say something good. Maybe.
Well, I'm just going to say if the probability of any event is 1, can happen, then the probability of the infinite disjoint events is absolute.
Wait, say that again? Step back. You want to hold on? Okay. We'll hold on. Oh no, I lost my train of thought. Yeah. Okay. So keep in mind here that in this definition, we don't necessarily relate all the events A1, A2, A3, all the way out to infinity. We're not saying anything about the coverage of these events in terms of the sample space, that they necessarily cover the sample space. It's just an infinite collection, right, of events. All right. So what you'll find is I always like these little proofs in the book, and I think they're a little bit fun to sort of get into the habit of learning some math. Okay. All right. So one of the things that we can do is we can show that the probability of the null set, again, which is nothing, right, that the probability of that happening is 0, which is a little bit weird, but that's fine. And so the way you derive this is actually just an application of this third axiom. Okay. So what we do is we just define A1 is equal to the null set, A2 is equal to the null set, and any AN, why am I doing that, is equal to the null set. Okay. We know each of these sets are disjoint because if we take any AI and we intersect it with AJ, right, we're saying what's the intersection of the null set and the null set? That's just equal to the null set, right? Nothing intersecting nothing is still nothing. Okay. So how does that help us when we apply axiom 3? Okay. So what this tells us, I might be using some abusive notation, so forgive me. All right. So we're going to take this sum of AI, of the probability of AI, and each one of them is going to be the same. So really, we're just taking the probability of the null set. And we're going to add it up infinity times, which is kind of like saying the limit as n approaches infinity of n times the probability of phi. Okay. So we know one other thing, which is our probability is effectively bounded above by 1, right? We can't get anything. Well, first of all, the null sets, right? If you take the union of the null set, you know it's less than the whole sample space, right? And so what you know is that this has to converge. All right? And the only value for this probability of phi that converges for any value of n is 0. Okay? So for limit to converge, the probability of the null set is 0. Okay. So that's kind of a neat little property. Okay. So again, this third property becomes really useful. Actually, the combination of these two, of the third property and this probability of the null set is 0, becomes useful if we want to show that instead of taking the sum of probabilities for an infinite set, we're just taking it for a finite set. Okay? So let's say we have k sets, right? So from A1, A2, A3, all the way to AK. What we can do is we can actually start But, we take A1, A2, A3, all the way to AK as they are. But then we define AK plus 1 is equal to phi, AK plus 2 is equal to phi, and in fact, let's say A to the K plus I is equal to phi for all I greater than 0. Right? All right, so I is just some positive integer. So in that case, we can now apply axiom 3. All right. So really we have the probability of A1 union A2 all the way to this union of A where, no, that doesn't really make sense. We have an infinite collection. I don't know how to write that. Let's just write it here. So the sum of I equals 1 to infinity of the probability AI. All right, so we can divide this up into 2 chunks. One will be for the set A1 through AK that we already have. And the other chunk will be for this infinite set. The remainder of the infinite set, where each event set is given by the null space. Or the null set, sorry. Now we know each one of these AK plus J's, so everything beyond the kth set is just equal to phi. So this is equal to phi. So the probability of this thing is equal to 0. And if we take the sum of 0, then we're just left with 0. And so that's how we end up with the idea that the union of k sets is just equal to disjoint sets is just equal to the sum of their probabilities. It's a neat little proof. It's kind of fun. Alrighty. This ends up leading to a few other nice properties. And we can sort of see it in a simple heads-tail example. All right, so I'm flipping a coin. My sample space is heads or tails. From the property above, right, in the axioms, I already know that the probability of the sample space is 1. And I know that heads and tails are disjoint events, right? They can't happen at the same time. All right, it's either one or the other. And because these two things span our sample space, right? They cover the whole area. We can say that the probability of our sample space is the probability of heads plus the probability of tails. Just shuffling things around, that leads to the probability of heads is equal to 1 minus the probability of tails. Now in this case, heads and tails are defined according to a coin, but there's no reason why we can't just have it being some arbitrary event A, right? And then the complement of that being A complement, right? Because we know that for any sample space, that's given by the union of A and A complement. And so we can still apply this same rule. And so this rule always applies, right? So more broadly, the probability of some event A is equal to 1 minus the probability of the complement of A. So this is a very useful rule. Yeah, so if I ask you, or I tell you the probability of Detroit beating Oakland next week if they played is 70%. Right, so Detroit beating Oakland. I could ask you, what's the probability of Oakland beating Detroit? It would just be 1 minus 0.7. Okay? So it'd be 1 minus the complement. All right. So what does probability really mean? Who knows? I don't know. People have different ideas of it. Generally, the one that most people go with is that probability is some sort of measure of the long run relative frequency at which something will occur. Okay, so the example of this is that they give in the book is, I'm mailing a package between San Francisco and LA, and I want to know, or I'm going to measure like how often that package is received within one day. Okay, so I do it a whole bunch of times. All right. And what you can do is you can divide the number of times it got there in one day by the total number of times you mailed it out. Right? And so in the long run, that fraction should converge to a specific number. Right? And so usually that's what people refer to as the probability. The big mistake that people often make is they, let's say the probability is 0.6. They take that to mean something like, actually, let me, this is wrong, right? The wrong thing to say is mailing out 100 packages, 60 will arrive within one day. All right, that's the wrong way to interpret probability. Okay, maybe in the expectation that is the case, but don't think of probability that way. Okay. Yeah, so this is usually the way people sort of work things out. They think about it as the long run probability. Now, it gets a little bit weird because a lot of times we assign probabilities without really being able to run an experiment for long term. Right? So what's the probability that you get an A in this class? I don't know. It's not like we can run that experiment 100 times. Right? So there's something a little bit weird about that. All right, to discuss probabilities for one-time events. At best, what we might do is we might just say, well, historically I give a third A's, so you have a 1/3 probability of getting an A. But we know that's certainly not the case because some of you won't study. So you don't really have a 1/3 chance, right? It's sort of, have you guys ever heard of Schrodinger's cat? Yeah, so there's a cat inside of a box, and I don't know. What ends up happening? What's the experiment set up? Yeah.
The whole idea behind the experiment is that unless you look into the box, there's no way you can tell it's dead or alive.
Yeah, you don't know whether it's dead or alive, right? But these are two absolute states, right? You're either dead or alive. Yet somehow we assign probabilities to them occurring, right? But the sort of joke is the moment you look inside the box, you collapse the quantum state. And so either the cat's dead or alive, and if it's dead, you effectively killed him, right? Where before it maybe had a 50% chance of living, by opening it, you now know it's dead, so it is dead, right? So, I mean, there's something a little bit odd about that, right? Which is the whole point of that sort of thought experiment. Is what does it mean to have a probability distribution that in fact gets realized, right? Yeah, all the mathematics is sort of derived according to these probabilistic states. Okay. All right. So we already, in doing the heads and tails problem, we sort of figured out this next axiom, right? Which is if you have some event, and the complement of that event, then their probability adds up to 1. Right? And we can use this really, really nicely when we have disjoint sets. Okay. Ooh. So this next proposition, the probability of any event is less than 1. Again, this is sort of logical, right? A is a subset of our whole sample space, right? That sample space at most has a probability of 1. And so if we're taking some subset of that, right, we're taking less elements, potentially less elements, right? So we would expect the probability to be a little bit smaller, right? And the amount that we decrease A is just given by A complement. Right? So if we remove, and if we don't account for all elements, then we're just removing that probability. Okay. Yeah. Okay. So this is probably the funnest one, I think, in terms of probability rules that comes up over and over again. It's this equation here, which basically says the probability of A or B is equal to the individual probability summed minus whatever they have in common, right? And it sort of makes sense because if I'm saying I want the probability of both these things, this area here, what I can do is certainly add up individually A, all right, and then individually B. There's A and there's B. But the problem is I double counted the part that they have in common. Okay. And so I need to make that adjustment here. So if I want to say, let's calculate A or B, it's just the probability of A plus the probability of B minus whatever we double counted. So this is actually a neat little, I don't know, it's a fun little proof if you want to go through it. Just a little hint there. Doing it for 3 sets is more or less the same idea, right? All you're really doing, so, this is the equation, we don't need to work through it, but all you're really doing is you're breaking it apart. So before you had sort of 3 sets, right? A, B, and C. And now you can start by sort of artificially making 2 sets, which is A and then B union C, right? And if you apply that first rule, this rule here multiple times, then you just end up getting the equation that we want. So it's just an extension of what we already know. Okay. All right. So when we start calculating probabilities, one of the simplest ways that we can do that for these compound events is to consider all the simple events that make them up. Okay? And again, if we had this rolling dice example, right? And again, so the sample space is 1, 2, 3, 4, 5, and 6. And I'm going to define the event A as rolling an odd number. Okay. The probability of rolling an odd number is just equal to the probability of rolling a 1 plus the probability of rolling a 3 plus the probability of rolling a 5. Okay. Where 1, 2, and 3 are simple events. Okay. They make up the events that are in A. Right. Now, we can actually use this property to calculate probability distributions. That should be a subscript. Why is this not a subscript? Okay. So this I should be a subscript, and this EI should be a subscript. Okay, so here's what we have. We have sort of like a train with 5 cars on it. And so we're trying to figure out, we have some commuter, some person who's about to get onto the train. And we want to calculate the probability that they get onto the first train, second train, third train, or car, or fifth train. We're going to define each of those as P1, P2, P3, P4, and P5. Okay, so P1 is the probability that the commuter gets onto train 1. P2 is the probability that the commuter gets onto train 3 or 2. P3 corresponds to getting onto train 3. Now we can be a little bit more specific and define each of the events. So E1 is commuter selects car I. Okay, so then what we're really talking about is P of I is just the probability of that particular event occurring. So the question here is we want to know what the probability of selecting each event is. So we have, if we think about our sample space, it's given by 1, 2, 3, 4, and 5. We also know that the probability of S is equal to 1, which is given by the sum of the probability of each event. So when we do that, that leads us to get the sum P1 plus P2 plus P3 plus P4 plus P5 is equal to 1. Right. Now in the problem, we have some sort of idea of how likely the commuter is to select any given car relative to another car. All right. So it says the commuter is twice as likely to select the middle car as cars 2 and 4. Okay, so we know P3 is equal to 2 times P2, which is equal to 2 times P4. Now, this sort of second statement is a little confusing, but basically what they're trying to say is that selecting P2 and P4 is twice as likely as picking P1 and P5. So knowing all this information, we can sort of do some back substitution in order to solve for each of these individual probabilities. So I'm sure I already wrote the solution there. Oh, maybe we can do that, yeah. So when we do those substitutions, right, so if we take this guy down, we're left with P1, right? P2 we know is twice P1. P3 is twice P2. So we get 2 times 2 times P1. Right. Plus 2 times P1 for P4. And then P5 we know is equal to P1. So we have P1 here. So we can add everything up. We know it still sums up to 1. And we get 4 plus 6. Is that what it is? 4 plus 4 plus 6? Or did I do that wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 P1. So this implies P1 is equal to 0.1. Okay, so the probability of picking this first car is 0.1. We can then back substitute and figure out what P2, P3, P4, and P5 are. Okay. And again, this was all done using the concept of simple events, right, to define some compound event, which in fact spans our whole sample space. So problems get really nice when the probability of any event is equally likely. So again, the canonical examples are sort of flipping a coin, right? If we have a fair coin, we expect heads and tails to be equally likely. Likewise, if we roll a dice, we expect 0, 1, 2, 3, or 6 to be equally likely. Or pulling a card out of a deck. In these cases, if I ask what is the probability of rolling a 3 or lower, all I need to do is add up the number of ways I can roll a 3 or lower, and then divide by the total number of ways I can roll a dice. Right? So for 3 and lower, I can roll 1, 2, or 3. Right? The total number of ways I can roll a dice are 6 different ways. So that makes life really easy if we want to compound, or if we want to calculate the probabilities for compound events. Okay? Because what ends up happening is each individual simple event, so if E of I is a simple event, the probability of it occurring is just 1 over n, where n is the total number of outcomes you can have. Okay. And so if we just want to calculate the probability of something complex, we're just adding the number of events that we have and multiplying it times 1 over n. This is the foundation of every problem involving poker hands, right? So if you guys play poker, it's always a lot of fun. And so it's all based on this, right? So all these probabilities that we'll deal with early on are based on counting techniques. So just try to separate them in your head, right? So whenever you're dealing with counting problems, like what's the probability 2 of y'all have the same birthday, right? Or what's the probability of drawing a full house, right? We're counting all the different ways things could happen. And the assumption is the probability is the same for each possible event, right? Pulling a queen is the same as pulling a 10 or a 5. Later on down the line, we'll deal with distributions where the probability of a simple event occurring is not equal. Okay? So a good simple example of this is, let's say I pick one of you, and I want to guess the probability that you own a dog, okay, versus a lizard. Right? So let's say everybody owns a dog or a lizard. Dogs are way more common, right? So the odds are it's a much larger probability for the simple event of owning a dog. It's not equally weighted. Okay? So please keep that in mind as we move forward with the semester. Okay. So let's talk about some counting techniques. So again, the reason why we want to do these counting techniques is because if we want to calculate some probability of a compound event A, then we want to know the number of ways that A can happen over the total number of ways that anything might happen, right? So we need to find quick tricks to calculate this numerator and denominator. Yeah, it's simple if we're talking like, did the package get to LA or not from San Francisco, right? Calculating how many different ways you can get an inside straight, that ends up being a lot more complex, okay? And so what these counting techniques are there ways to calculate the numerator and the denominator very, very quickly, or much quicker than before. And they basically provide the equations for you so you don't have to rederive everything. Okay. So the first one that we're going to consider is sort of a simple one. It's this product rule for ordered pairs. Okay. So the idea like this. Okay. So the idea is you have some ordered set of events, O1 and O2, right? Maybe it's rolling the first die and the second die. Okay. The first ordered event might have N1 options, while the second ordered event has N2 options. Okay, so the total number of possible combinations that you can get, right, or outcomes, is just N1 times N2. Right, so sort of the fun little example is, I have 5 shirts that I wear and 2 bottoms, right? So the total number of tops and bottoms combinations that I have is just 2 times 5. So I have 10 total outfits that I could wear. So sometimes it's written in a little bit of a tricky way, so I'll warn you guys to be careful. All right. So here goes a fun little problem. So some you just moved to a new city. All right, I moved to Orlando, and I need to pick out an obstetrician and a pediatrician for my family. Okay. There's 2 different clinics where I could do this, right? So we have clinic 1 and clinic 2. All right. Each has 2 obstetricians and 3 pediatricians. Now, the only deal is I only want to go to one clinic. I don't want to go to both. Right. Send my family to both. There's no point in driving across town. So how many different ways can I select an obstetrician and a pediatrician? Yeah. So we just have to be a little bit careful. Of course, the answer is 12, like the student stated. Who said that? 12. Who said 12? What's your name? Forrest. Forrest? All right, I'll try to remember you, Forrest. I remember you fall asleep all the time. So, but now I'll remember your name. It's fine. It doesn't bother me. The only thing that bothers me is cell phones. You can do whatever. Almost anything else except cell phones. That'll kick you out of class. Take a nap if you want to. Okay. So we have 12 different options. All right. The way we get that is basically if we go to the first clinic, we have 6 different options. All right. If we go to the second clinic, we have 6 different options. Right. And now it's just deciding which clinic do we go to. Right. So we get 6 options plus 6 options gives us a total of 12 options. All right. Now, one way you could sort of visualize this is by making a tree. So this is actually really common if we don't have any industrial engineers. But if you do stochastic optimization, trees are always really, really helpful. basically what you're doing, this bottom tree is for one clinic, so clinic 2, and this top one is for the clinic 1. And so obstetricians 1 and 2 are at clinic 1, and after you pick your obstetrician, right, you then pick your pediatrician, right? So obstetrician 1 is an option. From there, you can branch off and pick one of 3 pediatricians, okay? So people like developing these kind of trees. Now, if I didn't care about going to the same clinic for both doctors, then I would have a total of 4 obstetricians to choose from and 6 pediatricians. And so I'd have a total of 24 different options. Okay? So, again, just be careful of how the problem sort of stated out. It'll make life easier or harder for you. Okay. So, this product rule generalizes pretty nicely, just scales, right? So before we had 2 options, right? Obstetricians, pediatricians. If you have k options, you're just multiplying the number of choices in each option, right? So simple example, if I roll 3 dice, how many different ways can I roll 3 dice? Well, I can roll the first dice 6 different ways, I can roll the next dice 6 different ways, and I can roll the third dice 6 different ways. So I don't know what 6 to the third is. 200 what? 216. Okay, joy. All right, so we have our sample space, right? The number of ways that we can do that is 216. All right. So that actually leads to a nice little question, maybe. What is the probability? So I'm going to define some events. So what's the probability all 3 dice are less than 3? Okay. So if we want to do that, it's just the probability of this complex event is equal to the number of ways that we can get that event over the total number of ways we can roll 3 dice, right? So we already calculated the top guy, or the bottom guy, 216. So how many different ways can I roll 3 dice so that each dice is less than 3? 27. So how'd you get that? 3 times 3 times 3? Yeah. So we would just have 27 over 216. Okay, so it's just counting, right? Nothing too special. Okay. So things get crazy when we start talking about permutations and combinations. So I will readily admit I am terrible at permutations and combinations. It always weirds me out, especially because people use them in weird ways. So there's a problem, an example problem in the book about iPod shuffles. So when the iPod first came out, you guys were probably 5, but I was a teenager, right? And people used to always say, the iPod shuffle's not random, right? It's not randomly playing songs. It's always playing the Beatles, or it's always playing Metallica, right? Metallica has an agreement with Apple, right, to play their songs more often, right? And it ends up that we have a really warped perspective of randomness that cause people to think that, right? So I want you to look at the example problem They use permutations and combinations in a really weird way, to the point that I think it's really confusing. All right? But what I'm going to try to do in lecture is to not give you weird, tricky problems, right? That's not the point of this class, to give you tricky problems to solve. It's more for you to have an intuitive understanding. Whoa. That's weird. Intuitive understanding of what these permutations and combinations are and how to use them when we're calculating probabilities. Okay, so permutations and combinations basically deal with two basic premises, which is if we have a group of objects or events or whatever, how many different ways can we select subsets from that? Okay, so sort of the canonical examples are if you have a Little League team with 15 players and you need to pick your starting lineup. How many different starting lineups can you make? Now in this case, this corresponds to a permutation because the order in which you select the players to play the positions matter. Okay, so I might pick 9 players, right? But I have to assign one each to a position. And so here the example, we talk about Angela being pitcher and Ben being the catcher is a different lineup than Ben being the pitcher and Angela being the catcher, so flipping the roles, okay? So permutations take that into account. The order matters, okay? So the other example deals with combinations, right? And in this case, we're talking about, if this university bookstore, they want to display 3 laptops, but they have 10 options. They might randomly pick 3 to put out to display. Doesn't really matter what order they pick them in because they're all going up for display. The other example of this is like Powerball, right? I don't know, there's 60 numbers or however many numbers. Those balls can come out in any order. It doesn't matter, right? It's the combination of them that makes a winning number because they end up sorting it, right? You pick your combo numbers as sorted. So it doesn't matter what order the balls come out. Okay. Cool. All right. So when we're talking about ordered subsets, we're talking about a permutation. Actually, can I get your guys' opinion? I'm liking OneNote less and less. Would you guys prefer this as a PowerPoint? Or do you think this works?
I like you writing.
Writing?
Yeah, are you able to write on it if you're using PowerPoint?
Yeah, I can maybe do it.
Scrolling continuously through the notes, so you can just come back and forth.
Yeah, that's the nice part about OneNote, is that I can do that. In PowerPoint, I can't do that. It sort of ends up being a fail. I can write on the board, but then you guys won't have the videos. So that's why I kind of want to do it here. All right, what we'll do is next lecture, I'll try doing it in slides, and you tell me what you think. And we'll give a preference, but definitely, I will try to write more. Okay. Right now, we're just doing definitions, so it's not nearly as exciting. Okay. So for these ordered subsets, where the order actually matters and how we draw our items, it's called a permutation. Okay. I think one of the issues is the scaling. I really don't like it. Okay. So the way we denote the permutation is this P, K, comma N. Okay. Now, if order doesn't matter, right? So it doesn't matter what order we draw them in. In this case, it's called a combination. And it can be denoted 2 different ways. Similar to the permutation, we can use that notation, but instead of a P, it's a C. Okay. Or we can sort of use this parentheses notation, right? This is called like N choose K. Now, this always seems weird to me. It always seems backwards. So I have to force myself to say, from N options, choose K things, right? From 15 players, choose 9 to start the team. Okay, so that's the way I force myself to think about it over time. Okay, and so what these parameters are going to give you, it's going to give you the number of ways that you can do that. So again, this P sub Kn corresponds to the number of ways you can select K objects out of N where the order matters. Right? So give me a... Well, the CKN is the number of combinations that you get from N choosing K items. God, I hate that. It's so backwards. All right, so I think now's a good time to stop because this is just going to get hairy. Yeah, so let me ask a couple things. I messed up when I tried to re-upload your homework that's due this week. So you guys haven't seen it yet. Were all of you able to successfully do the homework and access the homework? Did anybody have trouble? Okay, good. So what I'll do is, because I'm behind in uploading the homework, it's not going to be due till next Monday, okay? Or Tuesday, I don't know. Tuesday, I guess. Doesn't really matter. And we'll just go a week from now. So again, I ask you guys, if you have questions, I'm more than happy to answer them. Don't email me personally, just put them on the web courses. Because trust me, you're not the only one with those questions. So on Thursday, we'll wrap up this chapter. And the way that I want you to think about this is we're going to do one chapter a week. I think it would be great if you were to try some of the reading, but I know most of you won't. So
we do need the book. Which of the chapters do you read?
So usually it will be all of them.
But what kind of schedule? Like one a week?
Yeah, one a week. So this week we're doing chapter 2. Next week we'll do chapter 3. Yeah, but I'll put a reading for each one because there will certainly be cases where some sections I don't care about. Okay?